Let us begin this lecture with a discussion of technological foundations for constructing quantum computers. Today, we have two basic types of quantum computers that we build. So the first type is superconducting quantum computers. And the second type is photonics-based quantum computers. Today, the superconducting quantum computers are more prevalent, but from my personal point of view, the photonics-based quantum computers are more promising in the long run. Let us discuss how photonics-based quantum computers can be built. Certain crystals are capable of emitting photons in pairs, and this pair of photons may be entangled. We can build lasers with these crystals, and then these lasers will emit entangled pairs of photons. In 2016, Chinese scientists launched satellite called Micius with a laser that emits entangled pairs of photons. And these photons are in maximally entangled state, 1 over square root of 2, and then vertically polarized plus horizontally polarized. This satellite will send each photon of this entangled pair to 2 ground stations. And the distance between these 2 ground stations was 1,200 kilometers. And the research team was able to confirm that these 2 received photons indeed form an entangled pair. The research team of the Micius project was able to carry out ground-to-space teleportation. So they succeeded teleporting single qubit, realized as an unknown polarization state of a photon. And they were also able to implement quantum cryptography, achieving quantum key distribution. Between China and Austria. At a distance of more than 5,000 kilometers. Current technology allows us to perform single qubit operations on polarization states of photons. In the Mach Zehnder interferometer, we have a beam of photons in some state, which is alpha times vertically polarized component plus beta times horizontally polarized component. And then this photon passes through the polarizing beam splitter, where the vertically polarized state will go along the upper trajectory, and the horizontally polarized state will go along the bottom trajectory. And so here the photon will be at once in 2 different places. Then the vertically polarized part passes through the phase shifter, where the phase of a photon is changed by some factor e to the I theta. And after recombination, so the new state will be alpha times e to the I theta times vertically polarized component plus beta times the horizontally polarized component. As a result, we get an implementation of the following quantum gate. So we have a quantum gate that operates on a single qubit, and it has a diagonal matrix e to the I theta 0, 0, 1. But here we have an additional degree of freedom in this experiment. What we can do is we can take this polarizing beam splitter and rotate it by an arbitrary angle gamma and perform the matching operation on this filter where we do recombination. If we do that, then we will obtain the following quantum gate. So we will get rotation operator R gamma times D times R gamma inverse, where R gamma is a rotation matrix cos gamma, sine gamma, minus sine gamma, and cos gamma. And now we have a two-parametric family of quantum gates. So because this D gate, the phase shifter, depends on the parameter theta, which is the parameter of the phase shift. And also we have the angle of rotation gamma for the polarizing beam splitter. So basically, we're changing from vertical horizontal axis to the coordinate axis rotated by angle gamma. And then it's not so difficult to see that these quantum gates will give us a universal system for computations with a single qubit. So if we take the unitary group U2, these are unitary 2x2 matrices that describe evolution of a single quantum bit. So this group is generated by a family of these quantum gates. So R gamma, D theta, R gamma inverse. So this means that every unitary 2x2 matrix can be written as a product of such quantum gates. Whereas we can perform arbitrary single qubit operations with photonics, we have a real difficulty implementing two-qubit quantum gates. In particular, we don't know how to entangle an existing pair of photons on the fly. So if we have a pair of photons that are not entangled, so we need a quantum gate that would entangle these photons. And currently, we lack such technology. What we really need is the controlled Mach Zehnder interferometer. Where the value of the first bit would control application or not application of the phase shift on the second quantum bit. This controlled phase shift will have the following matrix. So this will be a 4x4 matrix because we operate on 2 qubits. And on states 0, 0 and 0, 1, where the first quantum bit has value 0. So here we just have the identity matrix. And when the first bit has value 1, then we apply the phase shift. So we have e to the I theta and 1. If we can build a device that is able to implement this quantum gate operating on 2 qubits, then we will get a universal system for quantum applications. So it is sufficient to have this quantum gate and single qubit operations in order to implement an arbitrary quantum gate and thus construct a universal quantum computer. Currently, our success with building photonics-based quantum computers is very limited. And as of 2021, what we have is we have 4 qubit and 8 qubit photonics-based quantum computers. If we look at superconducting quantum computers, then currently we have superconducting quantum computers with many more quantum bits. The advantage of photonics-based quantum computers is that photons are cheap, can be operated at room temperature, and we have already quite developed technological base for interface between photonics and electronics. Next, let us discuss the technology used in superconducting quantum computers. These computers operate at extremely low temperatures, less than 10 to the negative 3 of a Kelvin, above absolute zero. And these computers could be fairly large. So they could have from 50 to 5,000 qubits. A clear challenge with superconducting quantum computers, because they operate at such a low temperature, they have to be very well isolated from the environment, from the ambient heat and the electromagnetic waves. When we see in the news an announcement of a new quantum computer with a huge number of qubits, we really should be looking at the small print. So that is, it is extremely important to know whether this quantum computer is able to complete the quantum algorithm before the quantum state disintegrates. Disintegration of quantum states is also known as decoherence. So protecting the quantum memory from decoherence is the principal challenge of superconducting quantum computers. Another major problem with superconducting quantum computers is that qubits are usually placed on a grid, and each qubit may be entangled immediately only with its neighbor. However, for most quantum algorithms, we need to be able to entangle any qubit with any other qubit. The restriction on connectivity of a quantum computer leads to a great increase in the number of steps required for completion of a quantum algorithm, and the result, there is a greater chance for accumulation of errors. Thus, creating a quantum computer architecture with much better connectivity is an important problem that needs to be solved. In a superconducting quantum computer, individual qubits are implemented using the quantum device which is called Josephson junction. In a Josephson junction, we have two superconducting wires that are separated by a thin film of an insulator. And the electric current across the insulator is possible due to quantum tunneling. In a Josephson junction, we have the following quantum phenomena. So we could have a DC current without any applied voltage. So provided that two superconductors on both sides of the junction have different quantum states or quantum phases. Another interesting phenomenon that occurs in a Josephson junction is that a constant voltage applied to the junction induces an alternating current. So this is known as voltage to frequency conversion. And there is an opposite phenomenon of frequency to voltage conversion, where an electromagnetic radiation of a constant frequency induces a DC voltage across the junction. Brian Josephson carried out theoretical work where he predicted the properties of the Josephson junction. And for his work, he was awarded in 1973 Nobel Prize in Physics. To implement a qubit, we take two low energy modes of current in the junction. One mode will represent a 0, and the second mode will represent a 1. And in general, we could have a superposition of two modes of electric current in the junction. In order to entangle two qubits, we take two Josephson junctions, and then we loop another superconducting wire around them. In this way, we can create interaction between two qubits. Another way to control Josephson junction is by applying external magnetic fields. The first quantum computer that became commercially available was manufactured by a Canadian company, D-Wave. And this computer came on the market in 2011. So this computer had 128 qubits. But this D-Wave quantum computer is not the universal quantum computer as we discussed in this course. Instead, this computer belongs to the class of quantum annealer or quantum optimizer. D-Wave quantum computers are designed to solve difficult optimization problems, and they belong to the class of adiabatic quantum computers. In order to understand the principles behind adiabatic quantum computers, let us discuss the following important physical problem in quantum mechanics, which is called the Ising model. In the Ising model, we take n particles with spin 1/2 and place them along the x-axis at regular intervals. So, for example, we can think that these particles are electrons. So, however, we're going to ignore the electric field interaction between these particles, and we'll look only at magnetic field interactions. So, for example, we will look at spin-to-spin interactions between neighboring particles. What will be the total space of states of this system? So, the space of states here is going to be a tensor product of n spaces. So, one space for each particle. And since we are dealing with spin 1/2 particles, so the internal space of states for each particle is the same as C2, or we can think that each particle is a qubit. We know that the spin state of an electron is a vector in a two-dimensional complex space. Recall that we have Pauli matrices as operators on a two-dimensional complex space. And what we'll do is we will denote by, for example, sigma zk. So this will be the corresponding Pauli matrix acting on kth component of the tensor product. And so as an operator, this will act as identity on all components except for the kth component. And on the kth component, it will act as the appropriate Pauli matrix. Evolution of any quantum system is given by the Schroedinger equation. And this equation is written in the following way. So we have I times Planck constant times the derivative of a quantum state with respect to time is equal to the Hamiltonian operator applied to the state of this quantum system. So the Schroedinger equation is a differential equation, and it describes evolution of the quantum state psi. The Hamiltonian operator that appears here, so this is a self-adjoint operator, which is specific to a particular quantum problem. This operator is called the Hamiltonian of the quantum system. Typically, we need to solve the initial value problem for the Schroedinger equation. So that is, we are given the function psi at the time t equals 0, and then using the Hamiltonian and this differential equation, we would like to determine the evolution of the quantum state for future times. How can we solve the Schroedinger equation? Since the Hamiltonian is self-adjoint, we can apply the spectral theorem and conclude that H has an orthonormal basis of eigenstates. And so let's denote that this basis by phi n. And the eigenvalues of the Hamiltonian are called energies. So each state phi n has energy En. And since H is self-adjoint, so these eigenvalues are real numbers. This says that any quantum system has a real energy spectrum. Next, we see that it is easy to write down the solution of the Schroedinger equation with phi n as initial data. And this solution will be the following function that we will denote phi n of t. So phi n of t is going to be exponential of minus I En t divided by Planck constant times phi n. We can easily verify by substitution in the Schroedinger equation that such a function will satisfy this equation, and at time t equals 0, the initial value of this function is just phi n. Then, to get the general solution of the Schroedinger equation, we follow the general approach of first-order differential equations. We take the initial data psi of 0 and decompose it as a linear combination of the basis functions phi n. So we write it as the sum over n of Cn times phi n. And then the evolution psi of t is going to be the linear combination of these functions phi n of t. So this will be Cn times exponential of minus I En t over Planck constant times phi n. So the conclusion of this discussion is that in order to solve the Schroedinger equation, we need to find the eigenvalues and the eigenvectors of the Hamiltonian operator for a given system. Let us write down the Hamiltonian for the Ising model. Recall that we have n spin 1/2 particles placed on x-axis, and we also embed the system into ambient magnetic field that goes in the z direction. And then we look at spin-to-spin interactions between these particles and also interactions with magnetic field. And the Hamiltonian has the following form. So this will be minus the sum, where k goes from 1 to n. We have hk times sigma kz. So this is the Pauli matrix acting on the kth component, minus j times the sum, where k goes from 1 to n minus 1. And then we have the product of two x Pauli matrix at locations k and k plus 1. Here, the first term describes interactions of spins with the ambient magnetic field, where hk indicates the strength of the ambient magnetic field. And in the second term, we have spin-to-spin interactions between neighboring particles. And here we neglect spin-to-spin interactions between particles that are further apart. So we take only nearest neighbors. The Hamiltonian here is an operator on this tensor product. So these matrices act on the corresponding components of the tensor product. So we get an operator on the space of dimension 2 to the power n. And diagonalizing a matrix of such a very large size is computationally non-feasible. So often we will have to resort to some qualitative analysis of this problem. We would like to find the eigenvalues and the eigenvectors of this operator. We will look at two simple special cases. In the first special case, we will have a zero ambient magnetic field. So this means that all hk coefficients are taken to be zero. In this case, we can easily describe the eigenvectors and compute the eigenvalues if we work in the x basis. So that is, we look at the two eigenstates that are aligned in the direction of x-axis. And so this will be the +1 eigenvector for sigma x. And we have the down x vector, which is the -1 eigenvector for this operator. Then the eigenbases for the Hamiltonian will consist of tensor products of all possible combinations of up x and down x vectors, starting with up x tensor with up x tensor up x and up x. Then the next vector will be up x, and then all the way, except where in the last component we'll have down x, and so on. So we have 2 to the power n vectors like this, and the last vector will have down x in all components. Let us compute the eigenvalues for these vectors. So here we're only looking at the second term, because the first term vanishes since we assume that the magnetic field is equal to 0. And then we have here a product of two sigma x operators, where the first one acts on the kth component, and the next one acts on the k plus 1 component. And each of these will have either eigenvalue +1 or -1. So we see that the product will have eigenvalue +1 if in kth and k plus 1 components the spin vectors are pointing in the same direction along x-axis. And if the spins are pointing in opposite directions, then the contribution of this term will be -1. In physics, it is very important to compute the lowest energy state of the system. And here we see that the lowest energy for this system is going to be negative, and the lowest possible value of the energy is obtained when all products sigma k times sigma k plus 1 have eigenvalue +1. This means that the lowest energy states will have no flips in their spins. And so we have exactly two states of the lowest energy. The first one and the last one. And so we conclude that the lowest energy in this system is minus j times n minus 1. So we have n minus 1 terms in this sum, and each term contributes plus 1. And we can easily see that the energy of a particular state is determined by the number of flips in the distribution of spins in these tensor products. So in particular, the highest energy will be the same expression with the plus sign, so j times n minus 1, and the states will be completely alternating. So we have up spin, then down spin, tensor up spin, down spin, and so on. And we will have one more state with the highest energy where we have an alternating sequence that starts with a down spin state. Let us now look at the second special case of the Ising model. So here we will look at a strong, constant magnetic field. So here we will assume that for all k, all hk are equal to h, and this value goes to infinity. So in this case, we can neglect the second term of the Hamiltonian because the first term will be the dominant one. So we'll assume that h is minus, well, we have a constant h times the sum. K goes from 1 to n, and then we have the Pauli Z matrix in kth component. In this case, the eigenstates for the Hamiltonian are described using the eigenvectors for Pauli matrix sigma z. So this will be tensor product states. So up z, tensor up z, tensor up z, and all possible 2 to the power n combinations ending with down z, tensor product with down z, tensor product with down z. And what we see is that this magnetic field will favor the first basis vector. So this basis vector will be the lowest energy state. And this lowest energy will be, so we have n terms, and each of them will come with a factor of h, so it will be minus n times h. And the last vector, where each spin is aligned against the magnetic field, so this will be the state of the maximal possible energy. And the maximal possible energy for this state will be the same expression, only with a positive sign, n times h. And for the energy of an arbitrary state in this basis, so we basically have to take the number of up spins in the tensor factors minus the number of the down spins, and multiply this by negative intensity of magnetic field H. So here we see the behavior of the Ising model in these two extreme special cases. But the general case, where we have arbitrary parameters hk, is quite difficult, and understanding the behavior of the Ising model, so for example the description of the ground energy states, is maybe very challenging. And now we come to the idea of quantum annealing. for a given difficult optimization problem, find the parameters hk of the Ising model so that the ground state, or the lowest energy state of the Ising model describes the optimal solution of the given optimization problem. Once this is done, and we have cast our optimization problem in the language of the Ising model, then we use our quantum optimizer, or this adiabatic quantum computer. We start with the trivial configuration, so with the strong constant magnetic field. And we initialize our quantum memory at the ground state of memory. So this means that in each component we orient our qubit along the direction of the magnetic field. And then we slowly tune the magnetic field to the required configuration so H1, H2, up to Hn. So these are the parameters of the Ising model that match our optimization problem. And then at the end of this process, the final state of the quantum memory will be close, or very close, to the ground state of the Ising problem we want to solve. And once we have this ground state solution for this non-trivial Ising problem that mimics the behavior of the optimization problem that we want to solve, then by probing this ground state, we will determine information about the solution of the optimization problem that we want to solve. This procedure is based on one claim, which is not very obvious. So if we start in the trivial ground state and then evolve our magnetic field to the required configuration, then why would the final state of our system will still be the ground state for the new configuration of the magnetic field? This is precisely the claim of the Adiabatic theorem that we are going to discuss next. So first of all, what is the meaning of the word adiabatic? So the adiabatic process means a process with slow evolution. So this means that we are going to change the Hamiltonian of the system, but we are going to do it slowly. In this theorem, we are going to deal with the Schroedinger equation, where the Hamiltonian is also time dependent. So we have IH, so d psi dt, is equal to the Hamiltonian that depends on time times the wave function or the state vector for our system that is time dependent as well. Before we give the formal statement of the adiabatic theorem, let us do some preliminary discussion of time-dependent Schrödinger equations. We saw that when we solve the Schrödinger equation, we have to diagonalize the Hamiltonian. And now this will be done in the time-dependent context. So this means that our eigenfunctions will depend on time, and so do the eigenvalues. So everything is now time-dependent. We will assume that the evolution of the Hamiltonian is continuous. Then it is possible to see that the energy eigenvalues are also going to be continuous. So indeed, so the Hamiltonian is a time-dependent matrix, or this is matrix-valued function, and we can look at its characteristic polynomial, which is determinant of lambda I minus h of t. And so then this characteristic polynomial will factor with ENs as eigenvalues. So we'll have a factorization lambda minus E1 of t times lambda minus whatever final index that we have, EM of t. If the matrix H continuously depends on time, then clearly the coefficients of the characteristic polynomial also will continuously depend on time. And then if we continuously vary the coefficients of a complex valued polynomial, then the roots of this polynomial will also vary continuously. So here we will assume that the roots are ordered. Well, since these are real numbers, so we'll assume that E1 of t is less or equal to E2 of t, less or equal to EM of t. So we're ordering the energy levels in the increasing order. So M here is the dimension of the space of states. An important assumption that we will make in adiabatic theorem is the existence of energy gaps. So this means that we assume that for all t, we have the difference between the j plus 1 energy and the jth energy level is greater than delta, which is greater than 0. So this means that in the process of our evolution, the energy levels do not collide. If we make this assumption, then we will be able to conclude that the eigenstate functions are continuous. Let us see why the assumption on the gaps between energy levels is essential here. Let us look at the following example. So let us take a time-dependent Hamiltonian, which is t 0, 0, 1. Then we see that this Hamiltonian has two energy levels. One is 1 and the second is t. And then we see that the lowest energy level, E1 of t, is given by t when t is between 0 and 1, and it becomes 1 when t is greater than 1. And then the eigenstate phi1 of t is equal to, so it's going to be E1 for t between 0 and 1, and when t is greater than 1, so this is going to be equal to E2. So what we see is that the lowest energy state here is discontinuous. It's equal to the vector E1 for small values of t, and it's equal to E2 when t is greater than 1. And the reason why this happens is that at t equals 1, the two energy levels will collide. And this assumption about the gap between energy levels will fail in this example. So this example shows that this assumption on the gaps between energy levels is important for continuity of eigenfunctions. Let us consider evolutionary Schrödinger equation where time parameter changes between 0 and 1, and the value of the Hamiltonian at t equals 0. So this is the initial Hamiltonian that we have. And the value of Hamiltonian at t equals 1 is some final Hamiltonian that we need to create. But next, we're going to slow things down. This means that instead of considering a Hamiltonian that evolves between 0 and 1, we're going to introduce Hamiltonian h with a t that depends on time, and which is the old Hamiltonian, h evaluated at little t divided by capital T. And here we see that this new time now runs between 0 and capital T. So we slowed the original process with the factor of capital T, and then mathematical interpretation of the word adiabatic will mean that we're going to let capital T goes to plus infinity. Let psi capital T of t be the solution of the time-dependent Schrödinger equation. With initial data psi t of 0 being the lowest energy state of the initial Hamiltonian h of 0. Assume the existence of a gap between the lowest and the second lowest energy level, that E2 of t minus E1 of t is greater than delta for all t. Then we're claiming that our solution at the final time, capital T, is essentially the lowest energy state of the final Hamiltonian. More precisely, we say that let phi1 of t be the lowest energy eigenstate for h of t. So in particular, phi1 of capital T is going to be the lowest energy eigenstate for the final Hamiltonian. Then our claim that the limit when t goes to infinity of the final solution of the Schrödinger equation minus the eigenstate for the final Hamiltonian times a certain phase is equal to 0, where this phase can be computed as the integral from 0 to capital T, I times the scalar product of phi1 of t with the derivative of phi1 of t minus t times e1 of t over Planck constant, and all of that integrated with respect to time. So this is the statement of the adiabatic theorem. Essentially, we are saying that if we have an evolving Hamiltonian and we start solving the Schroedinger equation with initial data being the ground state of the initial Hamiltonian, then our final state will be the ground state of the final Hamiltonian. More precisely, we can approximate the final state of the solution of the Schroedinger equation as the ground state of the final Hamiltonian multiplied by a certain phase shift factor, where the phase shift can be effectively computed. So two things are important here. So this evolution must be adiabatic, so this means that this claim holds only in the limit when the time of evolution goes to infinity. And the second important assumption is the existence of the energy gap between the ground energy level and the next energy level. This theorem may be generalized, saying that if we start not in the ground energy level, but at the kth energy level, then at the result of this evolution, we will be again almost at the kth energy level. And for that more general statement, we will require the existence of gaps between all energy levels in this system. But for the ground-to-ground state evolution, it's sufficient to have the energy gap between the first and the second energy levels. Without existence of such a gap, this theorem will fail, and it's easy to give examples when this happens. Let us sketch the proof of the adiabatic theorem. First of all, we write down the energy states for our time-dependent Hamiltonian. So we write h of t times phi k of t is equal to ek of t times phi k of t. So here time is between 0 and 1. Next, we take the solution of the slow Schroedinger equation and expand it as a linear combination of energy eigenstates. So we'll write the sum k goes from 1 to dimension of this quantum system, ck of t divided by capital T. We will also put a phase shift factor, exponential of I t mu k of t, and multiplied by the kth energy eigenstates, phi k of t divided by capital T. Here, the phase shift mu k is negative of the integral from 0 to t over capital T of ek of r over Planck constant dr. This formula is chosen in such a way that mu k has a prescribed derivative. So here we differentiate this integral with respect to parameter of integration. And then we see that this is negative of ek of t over capital T divided by t times Planck constant. Next, we're going to take this expansion of our solution and substitute it in the Schroedinger equation. And here, since the right-hand side is the product of three factors, then we will be using the product rule when we differentiate psi with respect to time. the left-hand side of the Schroedinger equation becomes, so we have I times H times, so the sum over K, and first we differentiate CK, and here we get the factor of 1 over T, so CK prime of T over capital T, times the other two factors. So we have exponential of IT mu K of T times phi K of T over capital T. Then plus. So the second factor is when we differentiate this exponential. So here we're going to get, so CK of T over T. And when we differentiate this exponential, we will need to take the derivative of mu. And so here it's written down. So we're going to get a factor of minus EK of T over capital T over TH times the factor IT from here times the same exponential and times phi K of T over T. And finally, the last term in the left-hand side we get from differentiating the phi K function. So we will get CK of T over capital T times the exponential times the derivative of phi K times 1 over T. And we equate this to the right-hand side of the slow Schroedinger equation, where we apply the Hamiltonian to this expansion, so essentially to these eigenstate functions. And we use the fact that these functions are indeed the eigenfunctions with eigenvalues Ek. And then in the right-hand side, we get the sum over K. We have Ck of T over T times the exponential and this is multiplied by phi K times Ek. And so here we get Ek of T over T, so because this is the slow Schroedinger equation, times phi K of T over capital T. This additional phase factor was chosen in such a way that the right-hand side will cancel with the second term of this expansion. So here we see that these two terms will cancel. So indeed, so here we have negative IT, and I times I is minus 1, so this negative sign will disappear. So then T will cancel here, and H will also cancel with the factor that's outside. And as a result, we will get simply the factor Ek exactly the same as in the right-hand side. So these two terms will cancel. And what we get is that the sum of the first and the third term are equal to 0. And now we can simplify this equation by moving the last term to the right-hand side. We will get rid of the factor IH, and we will also get rid of the factor 1 over T, which is common in both of these terms. And now we get the following equation, where on the left-hand side we have the derivative of Ck, and on the right-hand side we have the derivative of phi. Next, we take into account that our basis of eigenstates is orthonormal, and we take the dot product of both sides with the eigenfunction phi p of T over capital T. In the left-hand side, So since these functions are orthogonal, so we will have only one term that will survive this sum. So we get Cp prime of t over capital T times the exponential of it mu p of t. And when k is equal to p, so we assume that this dot product is equal to 1. So on the right-hand side, we get negative sum over k, ck of t over capital T times the exponential times the dot product of two functions. So phi p of t over t and the derivative phi k prime of t over capital T. To simplify this equation, we are going to introduce a variable s, which is t divided by capital T, and we are going to move this exponential factor to the right-hand side. So then we get that Cp prime of s equals, and so we get the differential equations on our coefficient. So here we get negative sum over k. So here we have ck of s times the dot product of phi p of s with phi prime k of s times the exponential of the difference of these two phases. And when we write this exponential, we will use our formula for the coefficients mu k. So we get exponential of negative I t over h times the integral from 0 to s of ek of r minus ep of r dr. Now, what is the claim of the adiabatic theorem? This theorem says that if we start at the ground state of our Hamiltonian, then at the end of the evolution, we will end up in a state which is close to the ground state of the final Hamiltonian. And this means that if we look at this expansion, so this means that we assume that at t equals 0, the coefficient c1 is equal to 1, and all other coefficients, ck, at 0, are equal to 0. And what we need to prove that for all k different from 1, the coefficient ck of 1, and this coefficient, strictly speaking, depends on t, is close to 0. So this means that all coefficients of these expansions that do not correspond to the ground state are being close to 0. This complicated expression that we derived is a differential equation for these coefficients. So what we can do is, so since the initial data is equal to 0, so then we can write that Cp of 1 is equal to the integral from 0 to 1 of Cp prime of s ds. And in this way, we can show that this coefficient remains small with the help of our differential equation. Basically, we need to integrate the right-hand side of this differential equation with respect to s and show that the result is going to be small for all p different from 1. To see this, we need to analyze the right-hand side. So here we have three factors. The first two factors are continuous with respect to s. And the third factor is the complex exponential. So this means that this function is going to be oscillating. And the major point to keep in mind is that the parameter capital T is very large. So this complex exponential is really a fast oscillating function. And then we have Riemann-Lebesgue lemma that says that if we integrate a continuous function against a fast oscillating function, then the result is 0 in the limit when the frequency of oscillations goes to infinity. Let us recall this result. Let f be continuous on the interval AB, then the limit when t goes to infinity of the integral over AB of f of s times exponential of I ts ds is equal to 0. In our case, we can't reference Riemann-Lebesgue lemma directly, because in the Riemann-Lebesgue lemma, so here there is exponential of its, and we have exponential of it and then integral from 0 to s. But it's quite clear that it is possible to generalize Riemann-Lebesgue lemma and make it applicable in this setting that we have. Then we can conclude that all coefficients except for the first one are close to 0. And actually this holds for all time. And they become 0 in the limit when capital T goes to infinity. So that is in adiabatic limit. And for the coefficient C1, we can write down the differential equation. So we have that C1 prime of S is equal to, so here, because all coefficients different from 1 are close to 0, so we're going to drop them. So we actually will write approximately equal negative C1 of S times, here we have phi1 of S with phi1 prime of S. And the exponential factor becomes 1. Because, so here we need to equate both k and p to 1, so this becomes 0, and we get exponential of 0. So we get this differential equation, which can be solved, and we can write down that C1 of S is equal to the exponential of minus integral from 0 to S of the dot product phi1 of r with phi prime 1 of r dr. And finally, we can write down our solution of the Schrödinger equation. So we can write down that psi t of t is approximately equal to, in the sum, we need to take only the first term because all other coefficients ck are small. So we have c1 of t over capital T, but here we have the expression for c1. So we have exponential of minus integral from 0 to t over capital T. So here we have phi 1 of r with phi prime 1 of r dr times this exponential here, so times another exponential, so which is another phase. So we have I times t times mu1, so which is minus integral from 0 to t over capital T of E1 of r over Planck's constant dr, and times the basis function phi1 of t over t. And in the limit, when capital T goes to plus infinity, we will have that the difference between the left-hand side and the right-hand side goes to 0. And basically, this proves that if the initial state of our quantum system is in the ground energy state, then during the evolution, as we adjust the Hamiltonian, it will stay in the ground state as well for all times. Here, it's important that this parameter capital T is large. So this explains why this process has to be adiabatic, so that is slow. So we are going to slowly change the Hamiltonian. And in order for this theorem to be valid, we need to have the energy gap between the ground and the second energy levels. This theorem provides a theoretical foundation for quantum optimization or quantum annealing. And so this is how these quantum computers work. In this lecture, we discussed one-dimensional Ising problem. For D-wave computers, the qubits are located not on a line, but on a two-dimensional matrix. And the Ising problem that occurs in the setting of D-wave computers is two-dimensional, but basically the same idea applies. So it's easy to find the ground state when we place the system in a strong magnetic field, and then we slowly relax this magnetic field to tune it up to parameters that will solve optimization problem that we need to solve. And the claim based on the Adiabatic theorem is that the final state of this quantum computer will be very close to the ground state or the optimal solution of our optimization problem. We need to point out that in order to apply the Adiabatic theorem, we need to have the energy gap between the lowest energy state or the ground state of the quantum system and the next energy level. And this gap needs to persist during the whole time of evolution. A priori, it is not quite clear how to ensure this condition. So we need to make sure that the first energy level does not merge with the second energy level. And it is not totally clear how to ensure this in practice. If the energy gap condition fails, then we might get a solution which is suboptimal. So it will be close to the optimal solution, but not necessarily the optimal solution. Quantum annealing allows us to solve optimization problems in very high dimensions. So because for quantum computers, the space of states has exponentially high dimension. And often this optimization problem will not be feasible to solve using classical computers.